Hello, and welcome to Agrosa Physics. Today is day 76, and what I'd like to do is solve another conservation of energy problem, but this time friction's involved, and we'll see how much more difficult it is when friction is involved. Remember, friction does work. It steals energy, and that means we're going to have to place it on the right side of the equation because the final conditions are going to be less than the initial. And in order to make the equation equitable, we're going to have to add that lost work to the right side of the equation. So let's get right to work. We'll take out the whiteboard now and we'll solve some conservation of energy problems with friction. Now we're going to do the same ski jump problem that we did before, but we're going to add friction to the problem. And friction is going to steal energy. So when we have our equation, which is PE plus KE equals PE plus KE prime, what will happen is the left side, the initial, will be greater than the final. So what we have to do is then add the work done by friction to the mix. Now, we also need to know, since the work done by friction isn't going to have a mass in it, we're going to need to know the mass of the skier, and the skier is 50 kilograms. Now, it's also not going to have a consistent amount of friction because of the curve. The normal force will change, so the amount of friction will change. So what we're going to do is assume for this problem that Fg equals Fn for the whole trip. And the entire trip was 315 feet. So the length of the ski jump itself is 315 feet, which we need to convert. 3.28 feet is 1 meter. Feet disappear. 315 divided by 3.28, and that's going to be 96.04 meters. So the ski jump itself is quite long. Now, if we go back to this part of the equation, remember, work done by friction means it's friction times the distance. It's work is force times distance. So how do we find friction? Well, friction is mu Fn. We need to know what gravity is first. Force of gravity is 50 times 9.8, and that's 490 newtons, which for this problem we're going to assume is the same for the whole trip. So the normal force is 490. Friction is mu Fn. Now, it said in the problem that this was wax skis on snow, so if we look at our reference table, we'll find that we have 0.05 for our mu, 490 for our Fn. So 490 times 0.05 is 24.5 newtons. Now, that's the force we're going to plug in for the F of force times distance. Now, we still have to think about what type of energy we have at the top so that we can simplify some of the pieces of the equation. It has potential energy, so we're going to have that term mgh plus the kinetic energy, if we start at rest, is 0, equals, if we call the bottom of the problem 0, potential energy disappears, plus 1/2 mv squared plus Fd for the friction term. All right, now the mass is 50 kilograms times 9.8 times 28.05 meters, and that's going to equal 1/2 50 kilograms v squared plus the force was 24.5 newtons, and the distance of the entire track is 96.04 meters. So, I already erased half of this, so let me just get rid of the friction term, and we'll keep working. Now, this first term is 50 times 9.8 times 28.05. We get 13744.5 equals 1/2 of 50 is 25 v squared plus 24.5 times 96.04. So that term is 2352.9. It's 9/8, so let's do this. 2353 At this point, we need to subtract a 2353 minus 2353. So 13744.5 minus 2353 is 11391.5 equals 25v squared. Divide both sides by 25 and take the square root. So divide by 25, square root is 21.35 meters per second. It's going to be less than it was when we didn't have friction, because friction stole some energy, so the kinetic energy at the bottom is going to be less than it was originally, and we have a slower speed. So a little more complex with friction involved, but remember, all we're doing is adding the work done by friction, which is force times distance, to the right side of the equation, because the initial is always going to be bigger than the final side. And that means we'll end up with our equality still. Well, here's a nice complex problem that we can solve using energy. Now we have an inclined plane, and we have a copper block riding on a steel plate that we've lifted to 37 degrees. The height is 2 meters above the ground. There's going to be friction involved between the block and the incline. So what we're going to need to do is realize that there is work done by friction as it moves down. Typically, we could just do the following. We could say the potential energy at the top is based on 2 meters of height, has no kinetic energy, and then the potential energy at the bottom is 0. So these terms would cancel, and we could find the kinetic energy at the bottom. Unfortunately, though, because of the fact that we have friction involved, we're going to have to add WF over here. Now, a few things we need to know about the block. It's 1.5 kilograms. And if it's going to have friction acting on it the whole length of the incline, we need to know how long the incline is. So what I'm going to do is sine 37 equals 2 meters over the hypotenuse. So that means 2 divided by sine of 37 will get me 3.323 meters. And that's the full length of the incline itself. That's going to be the D term when we deal with our friction later on. Now, speaking of friction, what we're going to need to do at this point is to draw a free body diagram. And that's good practice from before. We have the force of gravity down. We're going to have to break the legs of gravity and find F parallel and F perpendicular. F perpendicular is going to be equal and opposite to the normal force, which will allow me to find the friction. The only thing I'm missing here is the 1.5 kilograms. Now, this is copper and steel, so looking on the reference table, mu is 0.36 between copper and steel when it's moving. That's the kinetic friction. So let's find Fg first. 1.5 times 9.8. I'm going to get 14.7 newtons here. F parallel will be 14.7 times the sine of 37, or 8.85 newtons. And F perpendicular would be 14.7 times the cosine of 37, which is 11.74 newtons. So that value is 11.74. Now, typically what we do if we did this using forces, we'd find F parallel minus friction equals ma. We'd set up a kinematics equation after that and solve for the final answer. In this case, all we need to know is friction, because that's going to go here. The rest is going to be energy. So friction is mu Fn, which is going to be 0.36 times the Fn is equal to F perpendicular, 11.74 newtons. So 0.36 times 11.74 gets me 4.2264 newtons. Maybe a little too precise, but that's the numbers they gave me on the calculator. Now, at this point, what we're going to do is go back to our original equation. We have mgh for the potential at the top equals 1/2 mv squared plus fd. 1.5, 9.8 times 2 equals 1/2 1.5 kilograms. V squared, I don't know, that's what we're looking for. Plus friction, which is 4.2264. And the distance it acts is the full 3.323 meters. Now, if we look, there's only one unknown, and that's your V. So 1.5 times 9.8 times 2 equals 29.4 for that term. I'm going to combine these two and subtract it. So 4.2264 times 3.323, and I get 14.04 here. So 29 minus 14.04, 29.4 minus second answer. I get 15.3, we'll call it 356, equals 1/2 1.5 V squared. So now it's a matter of dividing by 1/2, dividing by 1.5, and then taking the square root. And you get 4.525 meters per second. Now you can go back and do this using forces from this point on and see if you get the same answer.